Everyone hear me? Okay, not too much feedback. There's a little bit of feedback, isn't there?
I will adjust you.
He'll adjust me. Okay, so let me. Adjusted? Can you still hear me? That sounds kind of quiet to me now. I'm not getting any feedback. Hearing me at the back? Okay, great. Okay, so today we're going to have a little bit of a change of pace. I've been trying to emphasize up until now sort of explicit classical approach to Hochschild and cyclic homology. You write your complexes down, you really examine the elements. And we did some explicit calculations of rings that came out of this construction like HP0. Today, as I say, we're going to have a change of pace. We're going to try to get from classical Hochschild homology to topological Hochschild homology. Which essentially means Hochschild homology over the sphere spectrum. So this is our goal. Essentially, we're going to delinearize and more derive the construction of Hochschild homology to get a richer theory that will be more interesting when we study rings of characteristic P or p-adic rings. So the first thing I want to try to do is to categorify in some sense, so that we can write it down in greater generality, our construction of Hochschild homology. That's so that we can adopt, let's say, a highbrow point of view, whatever exactly that means. Let's say a more homotopical point of view is what we want to do. So let's recall the structure that we had in our Hochschild complex. So write A tensor 2, A tensor 3, and so on. And although I gave this to you in the first lecture as a complex of K modules, I mean, it was really a complex that came from a simplicial K module. I had these two maps down in which I can multiply the first two elements or do it the other way around. And then I had three maps here by multiplying these elements or the next elements or the zeroth and the final element. And similarly, I've got some maps going up in the other direction by inserting ones. That gives this thing a structure of a simplicial K module, and we were looking at the related Dold-Kahn complex before. And then we had an action of Z mod 1 here, Z mod 2 here, Z mod 3 here, and so on. So let's, as I say, categorify what's going on here. So we say that a cyclic object, well, let's say in any category, so is the following data. It's a simplicial object, first of all. Let's call this X blob in C. So that is to say, we'll call it simplicial objects. That means I've got some functor from delta op, where delta is the simplicial category, to C. That's how we categorify simplicial objects. A priori means we've got a countable collection of objects and some maps between them satisfying some relations, but that's the same as saying that we have a functor from delta op to C. And then, so we need some more, such that each xn, so these are some objects in C, is equipped with some action by Z mod n plus 1, plus some axioms. So for example, we see in this case of the Hochschild complex, if I've got my string of elements and I multiply two of them together, so let me take my string of elements, let me rotate them a bit, then multiply two of them together, it would have been the same as first multiplying two of them together and then rotating, unless I happen to be multiplying some things at the very extreme, and then there'd be a difference. So you can see that gives some relationship between the phase and degeneracy maps and these cyclic actions in all the terms. And you can just write down what all the relations are that are satisfied there, and those are the axioms that we would ask to hold in general. So for example, since it's going to be the most important one, let me emphasize, I could look at this Hochschild homology complex. We view it instead, as I say, a simplicial. It's even a cyclic object in K algebras. And in fact, It's even better, it has a universal property there. So to be precise, if you look at all cyclic objects in K algebras, and you ask that the underlying simplicial object consists of A algebras, so you ask that the face and degeneracy maps are maps of A algebras, but not that the cyclic permutations are maps of A algebras, then this HH of A on K is in fact the initial object. So that gives a universal characterization of this Hochschild homology in terms of cyclic objects. And so I want to categorify this as follows, using what's called Kahn's cyclic category. So what Kahn showed was that there exists some extension of the usual simplicial category called lambda with the following properties. So firstly, it's got the same objects, and I'll write these as one usually does, as something like square brackets n. Oop, that's not right. As I vary over positive integers. But I add in lots more automorphisms. So in the simplicial category delta, there are in fact no non-trivial automorphisms of objects. And what I now do is I add in a whole bunch more, so my nth object is acted on by z mod n plus 1, and this is set up in such a way then so that cyclic objects in my category C correspond exactly to functors from lambda to C. So what you need to do that, well, you need to check these axioms and build these axioms into the composition law for the morphisms in this category lambda. And Kahn showed that there was a way to do that, so that if you've got some simplicial object, that should be at lambda op, so that if you've got some simplicial object, that is to say a functor from delta op to C, then it's going to admit this sort of cyclic structure, if and only if you can extend it up to lambda. And this is what we're going to use to make, let me box this, the circle appears. That's what's going to happen now, thanks to the existence of this cyclic category. So recall, so if we've got any category, we can produce a topological space. So I think of this category as being something of a combinatorial flavor, like delta, or like this cyclic category, though it could in fact be anything. We can associate to that a topological space, namely the geometric realization of its nerve. So I've got my category, and I look at the simplicial set in which the n simplices consist of chains of n composable morphisms in my category. That gives me some simplicial set. I then geometrically realize it by viewing the n simplices as being honest topological simplices. And that spits out a topological space from my category. And the key fact is that if I do this process to Kahn's cyclic category, which is classifying our cyclic objects, then what drops out is a classifying space for the circle. I should say there's really only one up to homotopy. For the circle. And this is proved more or less by a hands-on game of computing this this topological space. In fact, it does require a little bit of combinatorial work, but once you have, say, these axioms correctly built into the composition law in the category lambda, and use some general theorems for the calculation of the geometric realization of a nerve of a category, it drops out of some standard theorems. And the key consequence of this is that these sort of very combinatorial cyclic objects are closely related to the circle in the following sense. So if I've got some cyclic object, and the main case that we're going to care about is our Hochschild homology, but it's good to see it in general. So let's write this as x blob, and I now think of it, let's say, okay, cyclic object. Well, let me just say x blob in C. What does it give me? So it gives us an object, well, it's even a complex, but let me write it a little bit more categorically. Let's say an object in the derived category of K. So C has become, so I've made this a mess. Let me start this one again. So here's the consequence where I've got my categories right. So if I have a cyclic object, x blob, I don't want this to lie in any category, let me take it lying in K modules. That's the kind of case that we're familiar with from the Hochschild complex. A cyclic object in K modules gives rise to an object of dk, that is to say, just a complex equipped with an action by the circle in the sense that it will produce for us some functor, which I'd like to slightly distinguish from the original cyclic object. So let me underline it as a bit of fudge of notation. A functor from BS1 to dk. Now this needs to be unraveled a bit because it looks like an extremely bizarre statement. On the left, I have some topological space. On the right, I have some category. So fortunately, we understand these days how to make sense of such statements. We can put both topological spaces into the same world of infinity categories. So I will view this BS1 as a simplicial set, more precisely as some Kahn complex representing this geometric, representing the geometric realization of my cyclic category. And on the right, I should view this thing as a DG or as an infinity category. And then one can really make sense of the notion of a functor from BS1 to the derived category. But I'd like to, so I realize this is kind of a very frightening thing to see for the first time. So I'd like to make an aside and discuss the case of what happens in the case in which instead of the circle, I give you a finite group. Let's unravel what it means there and see that it's then a familiar notion of group action, and that we can write down from this point of view familiar constructions of group homology, group cohomology, and so on. And then we'll return to this fancier topological setup and just repeat the definitions. So this is, on the one hand, it's sort of an aside, but I think it's an aside which is pretty key to understanding what's going on if you're seeing this for the first time. So let's compare with the case G being a finite group. So then let's consider the same thing. Let's have a functor. I'll call it maybe not the same x because we'll come back to this. So why don't I call it y underline from BG to dk. So BG I can now think of simply as the category in which I have a single object, and the automorphisms of this object are given by G. So then the single object of this category, so let me say this is the data. So I've got to send the single object in BG to some complex. And then, as I say, in BG I have a morphism for each element of G. I've got to send this then to some action of a little g on my complex y, and these have to be compatible with composition. So in other words, I get exactly an action of G on Y. Or, so a helpful point of view when we return to this topological setup, I mean, saying that I have an action of G on my complex is the same as saying that Y can be given the structure of a module over the group algebra Kg. So in having done that, what do we normally do when we've got a group acting? I mean, I've taken a complex here, but you could imagine that this is in fact just some K module. I've got a group acting on it, and what do we typically want to study? We want to look at the homology and the cohomology of this action. So let's start with the cohomology. So I'll follow, say, the notation which is standard in the subject, one might call topologist's notation. I've got my complex or my module, I've got G acting on it, and I want to look at the invariance of this action, but I want to do so in a derived fashion. That's what group cohomology is. So we insert a little h for homotopy. I'm looking at the homotopy invariance, the homotopy fixed points of this action. So as I say, this should be familiar group cohomology, and from the point of view of seeing this as a Kg module, that means I'm just going to look at R hom over Kg from K to Y. That's the usual group cohomology. It turns out, though, and this is the formula that we'll need when we return to the more topological context, I can also represent this in a slightly fancier way. I can look at the limit over Bg of Y. So recall that we were encoding the data of this module or this complex with a G action as a functor from Bg to dk. That gives me a diagram in dk whose limit I can construct. And I need to do this in a sufficiently homotopically rich way, so I should take the homotopy limit, and that will represent for me the group cohomology. Then I can also look at the group homology. That is to say, I pass to the coinvariance for the action in a derived or homotopical way, which I can represent as Y tensor through Kg down to K, or I can take the colimit over this diagram given to me by Y underline. And then finally, perhaps less familiar, is the Tate cohomology, which for a finite group is a method of splicing together the homology and the cohomology in a manner which often appears, for example, in class field theory, which here is denoted by a Tate G. As I say, this is defined by splicing them together as follows. So I take the homotopy fiber, or that is to say, simply the cone of the map from the homology to the cohomology given by the norm. So in here I need to get really little. That's a G. I think I can't do this. I'm going to change pen and see what happens. I think that is G in G of G. So I sum up all the actions of all elements in my group. My group is finite. And that defines for me the norm map, which you may have classically seen, gives you a map from the homology to the cohomology. And by splicing these together, that is to say, taking the cone of this, I construct the classic Tate cohomology of my group acting on some module. So that's the end of the digression in the case of a finite group. Let's now get back to the case in which my group is instead S1 and see what happens if we try to mimic a little bit these constructions that we've just seen in the finite case. So our cyclic object, x dot, gave rise to this functor from BS1 to dk, and we see in a similar way that this is the data essentially of the following. Well, firstly, I have some distinguished vertex in the classifying space of the circle, And this will get sent then to some chain complex sent to some chain complex over K. And what will this be? Well, if one chases the construction, which I didn't explain, of how the cyclic object gives rise to this functor from the classifying space to the derived category, this chain complex will be, well, in fact, it will be, I'd like to say it will be, in fact, the X blob that we started with, but I should be a little bit more precise. I should say it's Dold-Kahn of X dot. So I started with let's say a simplicial K module, and any simplicial K module gives me a chain complex. I can turn it into a chain complex via this Dold-Kahn construction. And that will be the chain complex which is appearing here. What's more interesting is that it's equipping it with some module structure over what? Well, my analogy with what we had before should be a module over Kg, that is to say Ks1. It's another one of these bizarre expressions. I'm writing down group algebra of some topological group. So what do I have in mind when I write this? Well, I define it to be, let's say, one way to represent S1 as a topological group is as the simplicial group Bz by applying bar construction to the integers. So if I have a simplicial group, then I can form the simplicial group algebra KBZ. Or if I choose to view this as a differential graded algebra, any simplicial algebra gives rise to a differential graded algebra, this will be something very simple, either by explicitly calculating it or by appealing to some calculation of the homology of the circle. This will look like K of epsilon mod epsilon squared, where epsilon is in homological degree 1, and there's not really space for any interesting differentials. So now what does it mean to give some complex the structure of a module over K epsilon mod epsilon squared as a differential graded algebra? It just means that I need to specify some map from the complex. Sorry, that's now chain. Let me give this thing a name. This chain complex, I guess, should be called X, which is some of the underlying chain complex of the simplicial object. And then this is an X. So becoming a module over K epsilon mod epsilon squared, I just need to specify what epsilon's doing, and it's giving me some map from the complex to its shift. And that's nothing other than Cons operator B that we saw previously in the case of Hochschild homology. So this highbrow point of view of being an object of the derived category equipped with an S1 action, that is to say, functor from BS1 to the derived category, is a fancy way of encoding the data of some complex and the extra data of this morphism that we saw previously as Cons operator. And so now in this context, we can mimic our definition of group cohomology, homology, and the Tate cohomology that we saw in the case of a finite group. So I can define the homology of the action of S1 on my complex either as, let me first write down sort of the algebraic point of view. That follows, or, and this will be the better point of view once we pass soon into the topological setup, I return to the point of view that this object with S1 action is really a functor from BS1 into my category. Yes?
So does being a module over K epsilon or epsilon square also capture the Cn action?
Yes. Somehow they're the same up to homotopy. Yeah. So we can mimic these earlier definitions, and I can define the cohomology of this circle action on my complex, either in an algebraic way, or as I say in this more topological fashion of taking the limit over the diagram indexing my object. And similarly, we can form the homology of the action, that is to say the derived coinvariance, either by taking a derived tensor product in the world of differential graded modules, or by taking a colimit indexed over my diagram of the object defining this S1 action. And then finally, one can also define so-called Tate cohomology, even in the generality of this circle action, which becomes a little bit more complicated because the norm map, well, you can't write down an infinite sum of all elements of the action of your group G, but it turns out that there still exists some norm map from the homology to the cohomology, except there's a little shift involved because the circle is not a discrete group. I think I don't want to get into that so much. And so these produce for me, by mimicking these definitions in the case of a finite group, the moment some complexes, which as I say derive to be called the homology, the cohomology and the Tate cohomology of this circle action. And these, in fact, are things that we've already seen. That's the key point. Let's have a new piece of paper for it. So if this cyclic object that we started with was the Hochschild homology of some algebra over K, well, so that's giving me particular setup in which I can apply this formalism. So I pass to the S1 cohomology, and that will be nothing other than this negative cyclic homology, which we described explicitly before. And if I pass to the S1 homology, I'll get the cyclic homology. And if I do this Tate construction for the S1 action, then I'll get the periodic cyclic homology as I defined it before. And then this sequence here, splicing together the periodic cyclic homology, splicing together the Tate construction as the homology and the cohomology, is nothing other than the norm sequence that we saw previously, splicing together the periodic cyclic homology in terms of the other two theories. So let me try to give some idea of where these equivalences come from. So let's go back, for example, I think the easiest one to see is if we do the case of cyclic homology. So let's analyze this formula a little bit here. So recall that this group algebra KS1 is nothing other than K epsilon mod epsilon squared, where epsilon is sitting in homological degree 1. So to compute a derived tensor product like this, I've got to resolve K as a K epsilon mod epsilon squared module. And there's an easy way to do that. I just write down an infinite line of copies of K epsilon mod epsilon squared, and where the connecting maps are multiplication by epsilon. That resolves K by, in fact, 3 K epsilon mod epsilon squared modules. And so then when I come to compute this derived tensor product, what do? I write down infinitely many copies of X connected by multiplication by epsilon maps. But multiplication by epsilon is nothing other than this manifestation of Kahn's operator. So when I try to compute this derived tensor product, I end up with infinitely many copies of my complex X, that is to say my Hochschild complex, connected by infinitely many copies of Kahn's boundary map. And that's precisely the double complex that we wrote down to define things like cyclic homology, negative cyclic homology, and periodic cyclic homology. And so when you unravel those definitions and what these expressions mean, you recover these identifications of these highbrow perspectives in terms of S1 homology, cohomology, and Tate cohomology, and the earlier things that we wrote down in terms of as I say, very explicit double complexes. And so the advantage of having now adopted this more highbrow point of view is that we can repeat the construction in much greater generality. So to be precise, we may now replace, so what did, up to now we've been looking at some, say, K algebra, okay, and any K algebra, okay, in particular, okay, a K algebra is a K module, it's sitting in the derived category, this is the world in which we've been working. Take some K algebra, we constructed the Hochschild complex, or the Hochschild cyclic object, and that produced for me complexes. We can now replace this, let's say, by any algebra object in any, and now we can just start writing down as many adjectives as we feel are necessary to make the theory work. Say any rich enough, symmetric, monoidal, well, we want something of a derived flavor, derived or infinity category. And where we're actually going to do this is in the world of spectra. So let me first draw a little diagram so that we can adopt the right, at least the point of view that I want on spectra, and then I'll explain a little bit more detail on what I mean by repeating the construction. So up till now, we've mainly been looking at complexes. So we've been working in this derived category, and this is some, as I say, this is, what have we been using? It's some symmetric, monoidal, I want to be able to tensor things together. Well, it's stable, that's maybe, it's an important word. Infinity category. But what I really want you to focus on is that it's symmetric monoidal. We understand how to look at complexes. We understand how to pass between simplicial K-modules and complexes. That is to say, we can geometrically realize here. And the unit object here, that is to say, what we tensor over is K. But we're going to go from here to the world of spectra, which we can think of as being some derived category over the sphere spectrum, which is, again, has all the same formal structure, symmetric, monoidal, stable infinity category, so I can perform the same operations. But the unit object is now something more fundamental. It's this sphere spectrum S. And I can get from complexes to the world of spectra by restriction along a map from S to K. So this is the so-called Eilenberg-MacLane construction, at least if I started with DZ. But I want you to think about it in a very naive way, that over on the right-hand side in the world of spectra, we have this symmetric monoidal category in which we can perform all the same operations as we've been doing with complexes. And there exists a functor so that I can view this algebra K that we've been working with up until now as a spectrum, but it's no longer the unit object over there. I mean, it's completely analogous to if you're studying some algebras over the complex numbers, and you decide then, in fact, to start working over the real numbers. If you have any algebra over the complex numbers, you can view it as an algebra over the real numbers, and you can replace your tensor products over the complex numbers by tensor products over the real numbers. And in doing so, in some sense, you're doing something richer because you're recalling, I would say you're recording more information about the object. So we're going to do the same here. We pass from this K-linear world of complexes over K to this S-linear and therefore less, it's not supposed to rhyme, S-linear and therefore less linear world of spectra. So in particular, I wanted to emphasize, and let me bring this back, this restriction, of course, behaves nicely with respect to the symmetric monoidal structure, and therefore if I start with some algebra object on the left side, that is to say just some K algebra, it will produce for me completely formally an algebra object on the right side. But that's just the point that I was making before, that instead of tensoring things over K, I can now tensor them in the right-hand side, that is to say, over the sphere spectrum, which is a less linear operation. So in particular, I can therefore now form a cyclic object, I'll call it Hochschild homology, of A over S, and this is precisely the topological Hochschild homology of A. So I just repeat the formula that I had for this Hochschild cyclic object at the very beginning, but I replace all the tensor products that were appearing over K by tensor products in this category. In fact, I mean, as a warm-up exercise to getting there, you could make the observation that this Hochschild cyclic object that I write down, you could certainly write down without any difficulty for any algebra object in any symmetric monoidal category. It's formal. You write down A, you can write down A tensor A as soon as you have a tensor product, and when you have a multiplication map on your algebra object, then you can write down all the necessary maps appearing in that construction. And then you go one step further and say, okay, I mean, we could also replace tensor products by derived tensor products and write down the same construction for an algebra object in any symmetric monoidal sufficiently derived category. And that's all that we're doing here. And this, well, it should be clear from the notation, this is our topological Hochschild homology. So this is living in this world of spectra. And then I can repeat these formulae that we had for negative cyclic homology, and periodic cyclic homology in this context. So I can form THH of A S1 cohomology, THH of A S1 homology, and THH of A Tate construction, where I construct these according to the fancier limit and co-limit definitions of homology and cohomology. Those are the ones that continue to make sense in this degree of generality. So in this first one, by analogy with what we saw in the comparison with the classical theory, is called the negative, I'm never sure what order to put the adjectives, negative topological cyclic homology of A. When I pass to S1 homology of the action, this is not defined to be the cyclic homology. Sorry, not defined to be the topological cyclic homology. It doesn't have a good name apart from just calling it the S1 homology of the action. And this one is called TP of A. I mean, that's for historical reasons. And this one is called TP of A, is the periodic topological cyclic homology of our algebra A. And I want to emphasize here that although we could plug in some fancy algebra object on the right-hand side, that is to say some ring spectrum, I will really be mainly interested in the case in which one starts with some honest algebra. I would probably take K to be Z, so I can start in fact with any ring. This gives me an algebra object in DZ. I turn it into an algebra object on the right-hand side by this formal process. I take all tensor products in this less linear way in the right-hand side, and then I output these things, all of which are some spectra and some new cohomology theories encoding interesting information about my initial honest ring. In particular, I can take their homotopy groups to output THHN of A, TC minus N of A. Well, let me skip the middle one because there's no really good piece. Well, no, let's write it down anyway. Pi N of THH of A HS1 and TP N of A I can take, so if I start with some complex here and I send it over to the right-hand side, it has some homotopic groups which coincide with the homology groups if I view it as a complex. But when I have a more general object here, I can still take its homotopic groups as some replacement for the homology. And so this one here, that's the topological Hochschild homology. At least if I plugged in a commutative ring, which will be my main case of interest, these will all be A modules, and the rest of these will just be abelian groups. They don't get any more structure. So how do these compare to what we've been studying up until now? Well, again, I've just returned to this formal point of view. If I've got some place I can take tensor products, and I go to another place where I can take tensor products, then the tensor products in the second place, they map back to the tensor products in the... Wait, have I got that map right? Yes, they map back to the tensor products in the first place. And so if I construct the Hochschild complex in the second place, it'll map back to the Hochschild complex in the first place, just by pure formality of how tensor products behave. And so I'll get a map from my topological Hochschild homology groups back to my Hochschild homology groups, and similarly for all the other theories. And what's important about this, the point I want to make, is that this map will have kernel and co-kernel. That's not the end of the statement. Of course, it has a kernel and co-kernel killed by some integer n, which, let me write it like that, some integer n, which only depends on the index that I'm looking at. It doesn't depend on the ring that I plug in. In fact, it's a manifestation. This n is coming from the size of the stable homotopic groups of spheres. So it enters into the picture, and we know, fortunately, that these are all finite. And that finiteness produces for me this bound. And so, in particular, if A contains the rational numbers, well, I can just write, it is an isomorphism. Because then this is a map of A modules, in particular it's a map of Q vector spaces, and so if the kernel and co-kernel are killed by some integer, then in fact it was an isomorphism. So the conclusion to take away from this is that if you plug in some Q algebra, anything in characteristic 0, topological Hochschild homology doesn't have anything new to offer. But what we'll see is that it's very interesting if A is characteristic P or P-adic. The rough idea is the following. I mean, in the previous setup in which we were studying some FP algebras, I mean, all of our constructions, they were necessarily linear constructions. All the constructions were Z-linear, and so if we plugged in some FP module, then everything that was spit out by the process was still an FP module. Whereas we know that the most interesting cohomology theories, even for things over FP, don't consist of FP modules. I mean, we'd like, in fact, to define cohomologies like crystalline cohomology, which are defined over ZP. And we can never hope to spit out ZP modules if we input some FP linear things and we only do FP linear constructions. But once we pass to the world of spectra, I mean, our constructions, they all become less linear. And they'll be sufficiently less linear so that we can plug in something of characteristic P, and these theories like negative cyclic homology and periodic cyclic homology will output for us, in fact, ZP modules. And these will turn out to be crystalline cohomology. And then even more interestingly, if we stick in something of a p-adic flavor, we'll produce some interesting new phenomena coming from p-adic Hodge theory. So I'll finish there. Thank you very much.
Questions? Sure. I was wondering if you could say a little bit more about the objects at the bottom of that page for, for the people who are number theorists who've never seen.
Which page? I hope you're not pointing to the right page, are you? Oh dear.
Right, yeah.
I mean, I'm not the person in the room to ask.
Who else?
There might be someone who knows this very well.
Okay. Jen?
I have a very silly question.
I doubt that. I mean, in this, I don't think any question is silly. Please go ahead.
No, I was very confused by your definition of K adjoined S1.
Okay, absolutely. No, you were quite right to be. So I would define it as follows. I mean, let me say the following. Suppose I've got a topological group. So a reasonable topological group, it can be represented as, I can represent it simplically. I can represent it as the geometric realization of some simplicial group. And then I can just define, I mean, it works fine in this context, I've just defined this KS1, or K of a general topological group, to be K of the simplicial group. And so that outputs for me then some simplicial ring, which is now a reasonable object of algebra. And in particular, I could convert my simplicial ring into a DG algebra. And that's what I've chosen to do here. So I represent S1 as a simplicial group by BZ, the bar construction on Z. That gives me an honest simplicial ring, KBZ. And if you compute the associated differential graded algebra, which you can do quite explicitly, since BG is a very hands-on gadget, it will output K of epsilon mod epsilon squared. And so I would adopt that then as a definition of KS1, though undoubtedly one can adopt a more highbrow point of view on it.
Okay, any last questions? Okay, let's take a break and resume at 10:05. Thank you.